Why do AAA games have so few NPCs? We know they have the budget and some of the best game dev talent in the world, so why aren't we having cities that feel truly rich and alive? And you can't tell me it's simply not feasible when a game from 2014 can have this many NPCs. So what's the reason? Am I missing something obvious? You know what? I'm fed up with questions. I need some answers. Luckily, I got the opportunity to explore this exact topic for an upcoming game called Blackwood. One of the missions will take place in a subway that should be packed with people. So if you're wondering why games have so few NPCs and what it takes to simulate and render a large amount of them on screen, this video is for you. In order to render a large amount of NPCs on screen, we need to create them first. And if you're like me and don't have the artistic skills to do so, you seriously need to check Meshy AI. When it comes to creation of 3D models, I don't think there's an easier workflow. I can just upload a reference image and after a couple of seconds, Meshy AI will produce a clean 3D model that will perfectly match it. But even if you don't have a reference image, you can use their Nano Banana integration to create one right inside the tool. And this isn't some random AI tool I found online. It's already trusted by more than 10 million creators worldwide. If you haven't tried it already, now is the perfect time since a new foundational model just launched. It produces sharper edges for mechanical surfaces while maintaining smoother, more anatomically correct geometry for characters. And not only that, but it's perfect for games because you can tweak the desired mesh density of the model. Once you're satisfied with the result, you can import it directly into your game engine since Meshy already generated all the required textures for PBR rendering. I mean, you just can't ask for more than that. Now use the link in the description and enjoy a 50% discount for all new users. Also, you can catch Meshy at booth 941 if you're attending GDC this year. Thank you Meshy AI for sponsoring this video. Let's start by checking what we need for simulating NPCs. First, an NPC needs to be visible in the environment. Oh, hi Mike! Next, Mike needs to know how to get to his favorite waiting spot, so he needs to be able to navigate from one point to another. And even though Mike likes to glide everywhere, other NPCs don't. We need to give them the ability to move in a somewhat realistic motion. What else do we need? Ah yes, since Mike isn't the only one trying to commute to work, he needs to make sure he doesn't bump into anyone. And even though we all want to look like Mike, we can't. Everyone needs to look different. But since the game is still in the early stages of development, I got these placeholder models to play with. Last but not least, we need to keep focus on performance. Currently, if we run just the empty environment, we are hitting about 180 FPS, which is not bad for this early stage of development. That's already a bunch of things to implement. Luckily, the game is being developed in Unity, which has a lot of built-in tools that I should be able to use to tackle these areas. For example, I can use the AI navigation package to bake the navigation surface. This surface will provide NPCs with information about which areas can be walked on. Now I can set the desired target location anywhere on this surface and Mike will know how to get to it. Next, I use the Mechanim animator system to give Mike some lifelike movements. Oh my god, what have I done? I should now be able to just spawn a bunch of NPCs all over the environment and set them free. Well, there's good news and there's bad news. The good news is that everyone is moving kinda correctly. They're mostly successfully avoiding obstacles and each other while traveling towards their destinations. The bad news is that the performance took a major hit. Yikes. We're not even hitting the 60 FPS with only 200 NPCs. And if I crank the number to something like 500, it's completely unplayable. I guess this is one of the reasons why other games have so few NPCs on screen at once. The issue is that the engine is built with usability in mind and not with performance. On one hand, animations are easy to tweak and set up, but because of that, they're evaluated on the CPU for each NPC. And while the rendering setup is intuitive and flexible, each NPC renders separately, requiring a distinct draw call. And finally, while the suite of tools for creating walkable surfaces is straightforward and easy to use, its source code is unavailable and can't be modified. Since I like the flexibility that the built-in tools give me, I will use them only for the NPCs that are in close range of the player. Other NPCs that are a bit further away from him, I will switch to a much more performant, completely custom system. Of course, I don't have that system yet, so it's time to get our hands dirty. I decided to tackle the navigation first since everything connects to it. And to prevent rendering and animation affecting the performance too much, I temporarily swapped 3D models of NPCs with capsules. And let's see the performance cost of built-in navigation for 500 agents. It takes about 1.9 milliseconds each frame. This isn't too bad, but that's still about 12% of the whole time budget if we're targeting 60 FPS. I feel like we can do better than that, and I just hate the fact that I can't access the source code. So I started researching available papers on this topic and decided to use a flow field as a base for my navigation system. Here's the general idea behind it. First, I split the area into cells. Then, I find the desired destination of each NPC and the corresponding grid cell that holds it. Next, for each walkable cell, I calculate the direction that will lead an NPC towards this destination cell. Finally, each NPC can just follow the directions of each cell and he should be able to reach its destination. Now, you may be asking, but how do we calculate those directions? Dude, that's an excellent question. The way I did it was by first calculating the travel cost of reaching the destination for each cell. To do so, we start by setting the cost of traveling to the destination cell to the highest possible value for each cell. Since I'm storing the travel cost as an unsigned short, the highest possible value is 65,535. Then, we update the travel cost of the destination cell to 0, since this is the end goal we're trying to reach. Now, whenever a cell updates its total travel cost, all neighboring cells need to be updated. You may be thinking, how do cells update their travel costs? Wow, amazing question. A cell updates its total travel cost by finding a neighboring cell with the minimum total travel cost. Then, it sets its own travel cost to the neighbor's travel cost increased by the cost of moving to that neighbor. For this example, let's say that the cost of horizontal or vertical movement is 10, while diagonal one is 15. The whole process repeats until there are no more cells to update. At the end, we're left with a grid of cells filled with costs of traveling to the destination. To get the final movement directions, each cell checks its neighbors and sets the direction toward the one with the lowest total travel cost. After we've calculated all directions, we have everything we need to calculate the path. That's nice and all, but you may be thinking, is this even better than using Unity's built-in navigation package? Man, you're killing it today with the questions. Well, let's put it to the test. If you remember, the built-in solution took about 1.9 milliseconds for 500 NPCs. Let's see how our flow-field navigation stands. It takes about 1.3 milliseconds for the same amount of NPCs. That's more than 40% faster, but there's no reason to celebrate yet, since we've got an issue to solve first. The NPCs are not avoiding each other at all. They're just passing through each other. Yikes. There are a lot of already known solutions for handling complex collision avoidance cases which use a variety of different mathematical models and methods. However, since these NPCs will be further away from the player, I need something that would just approximate collisions, but do that really fast. So here's what I decided. Each NPC will have this awareness zone around them. When another NPC enters this zone, the NPC A will check its movement and predict if there will be a collision or not. In case of a potential future collision, NPCs will try to move away from each other. The avoidance force will be reversely proportional to the distance between the NPCs, meaning that the closer they get to each other, the stronger the avoidance force will be. Also, the direction of the avoidance force will vary based on the angle of the possible collision. And how does this look in the simulation? Well, let's see. Ooh, that's not right. After squashing some bugs, the NPCs are nicely avoiding each other and are not passing through each other anymore, which is just what I needed. But what happened with our performance? It took a major hit. Can you tell what is ruining it? Actually, there are a couple of issues. First, each NPC checks the position of every other NPC to determine if it's inside a collision avoidance range or not. This scales extremely poorly with the increase in the number of NPCs. However, you may remember that I've already encountered this issue in my fish simulation video. Just to refresh your memory, the solution was to divide the area into large cells, roughly 3 by 3 meters. Then, every frame, we place each individual into a corresponding cell based on its position. With everyone placed in cells, we just need to check local cells to find out the neighbors we need to check for the potential collision. Nice, one problem solved. The second issue is that I'm calculating the logic for each NPC on the main CPU core, while all others are just chilling in the background. In Unity, you can run your code across multiple cores by using the job system. To use it though, I need to make my code compatible with it. I need to use structs instead of classes. I have to use native arrays instead of lists. And since the data is copied into jobs, everything needs to be blittable. And of course, the navigational logic needs to be written as jobs instead of monobehavior functions. Well, this literally took me a couple of days. Let's just hope it was worth it. Remember, this was the performance from before, and let's see how we're looking right now. Damn, this is amazing. We just jumped from 35 milliseconds to 0.7 milliseconds. I think we can call this a major jump. Of course, our previous iteration had a huge bottleneck, so let's compare this with the built-in solution. From 1.9 milliseconds to 0.7, that's more than 2.5 times faster. Not too bad. However, while analyzing the current performance, I noticed something. The final step of applying the updated positions to the transforms is taking 0.28 milliseconds, or about 40% of the total navigation time. That's suspicious. And would you know it, even though the update is implemented as a job, it's still being executed on only one CPU. What? After a couple of hours scouring my code for errors, I started to lose patience fast. Kinda like Unity's stock is losing its value. Then finally, I found the culprit. Can you guess what it is? Basically, I overlooked this one sentence from the documentation. Unity will process transforms on the same CPU if they have the same parent. Just by reparenting the NPCs to the root of the scene, the job gets executed across multiple CPUs and the duration dropped from 0.28 milliseconds to 0.09 milliseconds. That's 3 times faster. Okay, let's see how much this has improved our performance. Damn, it only takes 0.39 milliseconds now to process everything. Incredible! That's about 4 times faster than the built-in system. I feel like I can push this a bit further, but I'm getting a bit tired from looking at these capsules all the time. It's time to tackle the rendering and animations. To improve the rendering, we can actually do quite a few things. The first thing we can do is to change how NPCs are being handled in the engine. Currently, they're just regular game objects with a bunch of components for rendering, physics and animation. This is the usual way of doing stuff in Unity, but not a very performant one. What we can do instead is completely remove them from the scene and just tell the GPU what to draw and where. Now, there are no NPC game objects visible in the scene hierarchy, so I can't select them, but they're still being simulated and rendered in the game. However, by doing so, we lost one optimization that happens under the hood with Unity's default rendering: frustum culling. It's an optimization technique that checks if something is in the viewport of the camera before sending it for rendering. The stuff outside of this camera view frustum will not be sent for rendering. This way, we don't render stuff that isn't visible to the camera. Also, it would be nice if we wouldn't render NPCs that are hidden behind walls and other non-transparent objects. This optimization technique is naturally called occlusion culling, since we're culling the occluded objects. Finally, there's no need to render NPCs with this amount of detail when they're further away from the camera, since we can't really distinguish them. It would be better if we would switch to a lower level of detail version and render it instead. I already implemented similar rendering techniques in one of my previous videos, and I was running out of time a bit, so I had to do this quickly. Luckily, there's already an existing asset that provides all of the required functionalities. It's called a GPU instancer and is perfect for our needs. The link is in the description if you want to try it out. I've imported it into the project and reworked the rendering logic to use the functionality from the package. Now, let's take a look at the current performance. Wow, this made a huge impact. Compared to the initial performance tests of the empty scene, it looks like our whole simulation with rendering is taking about 1.5 to 2 milliseconds of the frame budget, depending on the amount of visible NPCs in the camera frame. That's not bad if you ask me. With the rendering sorted out and the performance looking quite stable, I switched my focus to improving the general look of the simulation. Usually in a station, there are a lot of people that are just waiting for the train, and a lot of the time they form these little clumps. To implement them, I created a helper tool that eases placements of small crowds. It automatically places NPCs and joins some individuals into smaller groups to make everything look a bit more natural. Then, I manually placed some people around the environment while assigning them special animations like smoking, talking on the phone, or leaning against the wall. What really brings the final look to the next level is the variety of animations that you have at your disposal. I'm incredibly lucky that the studio has access to some unbelievable actors and animators that made my job so much easier. With that, Here's the current state of the simulation. As you can see, the game is running pretty smoothly and the scene feels quite populated and alive. Actually, performance-wise, I could add many more NPCs, but I didn't want it to feel overcrowded. Of course, the animations and movements still feel quite clunky and there's more work to be done to make this feel truly polished, but I wanted to focus on performance first, and since almost all major functionalities are implemented, in my opinion, this proves that performance shouldn't be the reason why AAA games feel empty. Now, you could argue that this simulation is only for a small area and that the AAA games have huge environments to populate with NPCs. However, this implementation can be easily scaled to larger environments. You see, I've even split the subway into multiple smaller parts that are connected with each other so that each part only takes care of simulating NPCs that are inside it. Large environments can be granulated in the same way. Of course, there are more moving parts in a large AAA game, but they also have more resources and people working on the game. But that's only my opinion. Let me know in the comments, what do you think? What are the reasons for having a very limited number of NPCs in games? Also, if you have some ideas on how this could be improved even more, please share them, I would love to check them out. I will continue to improve this simulation, so if you want to check out how it will look when the game comes out, go wishlist it. The link to the Steam page is in the description. Thank you for your time and I'll see you in the next one.